A problem we'll look at now is a beam that has an axial load on it. You'll notice that the beam has a wall restraint at both ends. It's an 8-meter beam. With a point load in the middle, we have a change in the cross-sectional area. And what we're asked to do is find the maximum value of that load P with a constraint that the maximum allowable stress has to be 100, can only be 100 megapascals. So in this problem, we draw the whole structure free body diagram. Right? We remove the wall restraints. We're going to look just in the axial direction. So I'm just going to highlight right there the red forces just in the axial. And so we have two forces on the exact same line of action. And we will only have one equation of equilibrium, one linearly independent equation of equilibrium to solve for those two unknowns. So we're going to have to use the constitution, the deformation of the material. And we're going to do that by superposition. So I'm going to take the actual beam, which is restrained by a wall on both ends. I'm going to choose a redundant force. In this example, I'm going to choose the force over there, which I've called F2, the force in the wall, the restraint force. So I take the wall away. I've now created a determinate structure. That determinate structure shows up twice. I'm going to add those two determinate structures together to get the actual structure up there. And I'm going to need to apply a constraint equation. Right there we have an unknown force F2. The right end of the beam is allowed to move. So let's highlight right here. I have U at 8 meters. And that's going to be in what we call structure 1. Here will be structure 2. Right? That also has a deflection at 8 meters. Back up here in the actual structure, right, that wall is a constraint holding the wall at 0. So this will unlock the superposition. We're going to need to constrain those deflections at the right end. So U of 8, right, by the principle of superposition, the actual is equal to the summation of these structure 1 and structure 2. So if I pick on the point 8 feet from the wall, I do that because I know the deflection or the movement in the horizontal direction is 0. So I have a constraint equation. So all I need is the deflections in the axial direction, both in structure 1 and in structure 2. So in structure 1, I've got an axial force P. Right, that axial force P is going to act only over the first 3 meters. The last 5 meters are along for the ride. I'm going to use the cross-sectional area of 2A. So there is my deflection or the movement in structure 1 at 8 feet, at 8 meters from the wall. In structure 2, I'm going to use the internal force. Right, we solve for the internal force along the length of the member by taking out the blue saw. So there would be our P of X. Right, there's our X coordinate. And so we would find that the internal axial force is constant. It's just going to be the value F2 over the first 3 meters over here. Right? I've got F2 times 3 meters over 2AE. Over the last 5 meters, F2, 5 meters over AE. So when I add those two together, I need to get 0. That will very quickly get me a nice answer for F2. And so the math looks like this, I've got 0 is equal to my first equation. I'm going to add to it the second equation. E's will cancel out. I just work the math all the way through, and I get an answer for F2, which in this case happens to be negative. And that negative would mean that the answer is in the opposite direction of the of how I drew it up here in my superposition. So that means F2 is actually going to the left. So if we just replace this answer. If we put that answer on our free body diagram, right, there would be F2. And so I'm ready to solve for the internal force now throughout the entire member. To do that, I'm going to cut it. I'm going to use the blue saw at X. I'm going to do it two places. I'm going to cut it between B and C. Right, that gives me a free body diagram that you see right there. A nice clean approach to solving for the internal force. There I find out that it's equal to 3/13 times P in compression. Right, I've always drawn this in tension whenever I come across an unknown internal load. Do the same thing over here between A and B. I'm going to cut it right there. That gives me that free body diagram. I do equilibrium on that, some forces in the x direction, and I end up finding that PAB is equal to 10/13P. So we've got two stresses we can calculate now. Sigma AB, which is going to be PAB divided by the cross-sectional area, which is 2A. So one constraint is that that expression needs to be less than 100 megapascals. So just solving for P, there would be my first requirement, that P needs to be less than that number. Right, for segment AB. For segment BC, I'm going to take the answer for PBC divided by the cross-sectional area. Again, that needs to be less than 100 megapascals. So I'll go ahead and solve for P. So there are my two constraints. I'm going to choose the one that governs. So the smaller of them is going to govern, and that would be up there in equation 1. So governing with 1, P needs to be less than 2.6 A times 100 megapascals. And at that point, just plug in what A is and make sure you get your units, police. It's always a good little hashtag. I like to do that in red. Units, police. All right, what a megapascal is. And we get our answer that P has to be less than 23.4 kilonewtons.